So what we're going to look at now is exponential functions. So we looked at exponential equations. Now we're going to look at the function and what it looks like as a graph. What are the characteristics behind an exponential function? Because it does look different from some of the other functions that we've looked at. So we've looked at linear functions, we've looked at quadratic, we've looked at cubic, we've looked at multiplicities and tangents, we've looked at radical functions that have restrictions in them, or rational functions that have restrictions in the denominators. So now we look at exponential functions. So we start off with an idea of exponential growth. Mallory's a research scientist discovering a bacterial culture that can strengthen the immune system. To find the growth rate, she isolates 5 cells and observes the following growth pattern. After 1 hour, there are 10. After 2 hours, there's 20. And after 3 hours, there's 40. So if we let t equal the time in hours, and n of t being the number of cells after t hours, so n is a function of time. The formula for n of t as a function of t can be written in the form n of t equals ab to the power of t. A and b are constant numbers, and they're both greater than 0. What are the values? So any ideas as to what a and b could be? Well, we can determine some of that. We write out our formula. What do I know at time 0? How many cells do I have? 5. So if I was to substitute in what I know, n of t is 5 cells when the time is equal to 0. So I have ab to the power of 0 is equal to 5. What do I know about anything to the power of 0? It's equal to 1. So then what's a equal to?
5.
A has to be equal to 5. And then if I take time 1, I know that a is equal to 5, so now I have b to the power of 1, which is just b, and that's equal to 10. So to get b by itself, I divide both sides by 5, and what does b equal? So my function becomes n of t equals 5 times 2 to the power of t. So I can use a dot between them, or I can use brackets. 5 times 2 to the power of t. So I can now use this formula, and I could determine how many cells there would be after 8 hours. I let t be equal to 8. So n of 8 would be equal to 5 times 2 to the power of 8. And tell me what that would equal. What'd you get?
1,280.
The other way that I could get it is I could extend this chart. 4 hours, there'd be 80 cells. 5 hours, 160. 6 hours, 320. 7 hours, 640. 8, and so on. But using a formula makes it a lot faster, right? After 12 hours, there are 20,480 cells. How many hours did it take to have half the amount?
11?
11 hours. Why 11 hours, Evan?
Because it doubles every time.
It's doubling each time. So now if we graph this, first of all, we need to look at our window settings. In this graph, what do my x values represent? What's my x variable? In the context of the question, what does the x represent?
Time.
Time. And I know my time starts at 0. So I'm going to back it up. I'm going to let it start at -3. And we can go up, let's say, even if we go up to 20 hours or 15 hours. That's probably good. How many bacteria do I start off with?
5.
5. So again, because I want to be able to see axes, I'm going to start like at a -5. But I know at 10 hours, or sorry, 12 hours, there's 20,000 cells. So my Y max is going to have to be a big number in order to be able to see the characteristics I want from the graph. So I'm going to go up to 25,000. And then my scale, I'm going to go up by 5,000, so I don't have a whole bunch of tick marks that are distracting. Now I have my Y equals. So I clear off any equations that I had. I'm going to have 5 times 2 to the power of x. And then I'll press graph. So what I see is I see a graph that looks like this. But it's hard to see this part of the graph. And why is it hard to see that part of the graph?
Because it's so small.
Because it's so small. So maybe I want to readjust my Windows settings. Maybe instead of going up to 25,000, maybe for now just go up to 1,000. Go up by hundreds. And now see what happens. Now when you do that, what you see is the graph actually is in the negative x quadrant. So it does start over here and comes through and goes up. So now I can get a better sketch. So I can draw my picture to go like this. Do I know where it crosses the y-axis? What's the value of x when it crosses the y-axis? 0. So if I let x be equal to 0, what am I going to get? 5. This represents exponential growth. It's growth because it's getting larger, and it's exponential because it gets larger very rapidly. If you start following these numbers, I'm at 1280, then I'm at 24, and then I'm at like 5,000, and at 12 hours, I'm already at 20,000 cells. So when you think of how many cells you would have after 24,000 or 24 hours, you're talking a very large number of cells. Okay? Then we have exponential decay. So this is before your time. Chernobyl. Chernobyl was a city in the former Soviet Union, and in 1986 there was a nuclear accident. So when they talk about nuclear power and they talk about the risks with it, it's because of what happened at a place like Chernobyl. The atmosphere was contaminated with quantities of radioactive iodine, and the radioactive iodine in these quantities causes the cells to become cancerous far more readily than in normal conditions. So at the time of the explosion, 32,768 units of radioactive iodine were released into the atmosphere. After 1 week, there was 12,384, then 8,192 in the second week. In the third week, 4,096, and it just kept getting less. So it says use T to represent the time in weeks and N of T to represent the number of units of radioactive iodine after T weeks. Complete the following equation of the function which represents the information given. So what I could do is I could figure out, well, at 1 week, there was 16,384 units left. And that's going to equal 32,768 times something, we're going to call it n, to the power of 1, because the time would have been 1 week. 32,768 n. So to get n by itself, I would divide both sides by this 32,000. So what is this 16,000, whatever, divided by this 32,000? One half. Now, does it seem like the amount of units that I have after each week is going down by half? Yeah. So now if I graph this, or sorry, first of all, before we graph it, let's determine how many units would be left after 14 weeks. So I'd have n of t, so n of 14 would equal 32,768 times 1/2 to the power of 14. So when I go to put that into the calculator, 32,768 times bracket 1 divided by 2 bracket to the power of 14. How many units after 14 weeks? 2 units. So how many units would I have after 15 weeks? 1. And then I would have 1/2. How many units would I have at 13 weeks?
4.
How many?
4.
4. Okay. So now if I go to graph this, these are my window settings that I want to use because my numbers. So -1 to 8, negative 30,000 to 64,000, going up by 1,000, and then my y equals 32,768 times 1 divided by 2 in brackets to the power of x. And if I go trace and 0, so letting the time be equal to 0, where's my y-intercept? Where does it cross the y-axis?
32,768.
Which is that a number that we get in the equation. This is considered exponential decay. Decay because it's getting smaller. And I guess actually when I draw this in, why would I put this part of the graph as dotted lines? What does t represent?
Time.
Time. And this is time in weeks after the explosion. So do I have negative time in this case? No. And the only reason, like in the question or in the graph, it shows it in this type of pattern. So the other thing too is I don't have negative time, and this amount of radioactive iodine being released in the atmosphere was not more before the accident happened. So an exponential function can be written in the form y equals ab to the power of x. In this form, a cannot be equal to 0, because if a equals 0, the whole thing equals 0, and I no longer have an exponent. B has to be a positive value. It has to be a number greater than 0. We do not deal with negative bases. And then the exponent, or sorry, and it can't be equal to 1. Because what's 1 to the power of anything? 1. So then I wouldn't get an exponential function. So b has to be positive. It can't be equal to 1, but it can be anything else. Okay? And then x can be a real number. So what we're going to start working on, and I'm going to give you time to work on these, is to graph this So if we look at question 8, comparing the graphs of y equals 2 to the power of x and y equals 1/2 to the power of x. So in this equation, y equals 2 to the power of x, what is the value of a and what is the value of b? A is 1 and b is 2. If it's supposed to be written in this form, what would a and b be? So now if I look at this equation, what would be the value of a and b?
A be 1 and B be 1/2.
Right. So what I want done before we meet again is I want you to sketch the graph of the function using the table of values. So the best way to do that would be to take your calculator and type in 2 to the power of x and then go to your table of values. So second table, and then look at what your values are. For your negatives, like -3, take this number of 0.125 and change it to a fraction. Okay? So then you're going to write those numbers in this table, and you're going to graph 2 to the power of x, and then you're going to do the same thing with the 1/2 to the power of x, and you're going to plot those points. I would suggest maybe using 2 different colors so that you can see the difference between the graphs. And then looking at D and E. So on our next class, that's where I'm going to start from, is assuming that this is done, and I'll go through it very quickly. So if we take a look at our table of values with our graphs, we have y equals 2 to the power of x. And what I asked you to do is keep these in fractional form. So if x is equal to -3, I get 1/8, 1/4, 1/2. When x is equal to 0, 2 to the power of 0 is 1. And then I get 2, 4, 8, and 16. Now if I sketch this graph, I let my y values, I've got 2, 4, 6, 8, 10, 2, 4, 5, and then I go 1, 2, 3, 4. So when x is equal to 0, and then I have -1, -2, -3, -4. So I get 1/2. 1/4, 1/8. So my graph looks something like this. And this becomes y equals 2 to the power of x. So now if I've got my 1/2 to the power of x, and I look at my table of values, I get 8, 4, 2, 1, 1/2, 1/4, 1/8, and 1/16. So in this case here, when x is equal to -3, I have 8, 8, and then I have 4, and then I have 2, then I have 1, then I have 1/2, 1/4, 1/8, 1/16. So this graph this time looks something like this. And this is my y equals 1/2 to the power of x. So now if we look at summarizing based on my observations, again, the idea of an asymptote, what I have here with these two graphs is I have that the graph never gets into negative y values. Because no matter what my value of x is, my y value is always positive. Because as an exponent, when x is negative, it ends up being the flip of that to make that positive value. So in the equation of the function y equals 2 to the power of x, the domain of that function is that x could actually be anything. There is no one value that x cannot equal, that I can't find x to 2 to the power of x. The range are all my positive values. So y is greater than or equal to 0, and y is a real number. The graph does not have an x-intercept because it doesn't cross the x-axis. The y-intercept is 1, and the asymptote is the x-axis, which is the equation y equals 0. So then in my graph of 1/2 to the power of x, I have the exact same characteristics. X can be anything. The y values are greater than or equal to 0. Actually, it's not even greater than or equal to 0. It's just greater than 0. So y is greater than 0. And the same thing with this one. Y is greater than 0. There is no x-intercept because the graph does not cross the x-axis. The y-intercept is 1. And the equation of the asymptote is that y equals 0. 2 to the power of x, if I were to use the word as a growth or a decay function, 2 to the power of x is a growth function because the function is getting larger as the value of x increases. Whereas 1/2 to the power of x is a decay function. The function decreases as the value of x gets larger. So now what I would like you to do, if we look on the next page, is I would like you to pause and take a moment to graph these 4 functions and then sketch them so that we can see what the value of b does to my graph. So I'm going to give you a moment, and when you turn it back on, the 4 graphs will actually be in place. So once you're done graphing these 4 graphs, what you should notice is that this b value is affecting whether or not the graph is a growth or a decay. So it's a growth value when my b value is greater than 1, and it's a decay when it's that fraction between 0 and 1. The other thing that you may have noticed is that the graph always seems to go through this point of 0 and 1. So the value of b affects the steepness of the graph. As the value of x increases, the steepness increases. So when b is greater than 1, the graph blanks more sharply as x or as b increases. It actually rises more sharply. And when b is between 0 and 1, which are these two, the curve blank more sharply as the b value decreases. 1/10 is smaller than 1/3. It falls more sharply. So question C says, without using a graphing calculator, predict where you think y to the y equals 5 to the power of x would be, and where y to the 1/5, or sorry, not y to the 1/5, y equals 1/5 to the power of x would be. So 5 to the power of x is going to be somewhere between 3 to the power of x and 10 to the power of x. And that's really all we need to draw it, is that showing it that it's somewhere in between. It doesn't have to be in the exact center, it just has to be between those two values. And then my y equals 0.2 to the power of x. If I change that to a fraction, 0.2 or 2/10 is 1/5. So 1/5 to the power of x is going to be between my 1/3 and my 1/10. So this is y equals 1/5 to the power of x. And then what you can do is you can double check this using your graphing calculator. Question E says, state the x-intercept for each of these graphs. Where does the graph cross the x-axis? It doesn't. There is no x-axis. Where does this graph cross the y-axis? It's consistently crossing the y-axis at the same point, which is at 1. The domain. With any of these graphs, were there x values that x could not be? Were there any non-permissible values? And the answer to that is no. X could actually be anything. So the domain for each of the graphs is the set of x values such that x could be any value. X is an element of the reals. The next part is stating the range. What are my possible y values? Well, my y values are all the positive values for y. So in this case, it's the set of y values such that y is greater than 0, not equal to 0. Because 0 ends up being that horizontal asymptote. The graph gets very, very close to 0, but never actually crosses the the x-axis, the line y equals 0. So the next thing that I would like you to do on the next page is we're going to investigate what is the value of a due to the graph. So what I want you to do is I want you to graph these 4 equations and sketch them. Again, you're going to pause, and when you play, the 4 graphs will be up on the screen labeled. So before I reveal the 4 graphs, the question is, what does that number in front of that, or that a value, do to the graph of an exponential equation? Well, the answer is it impacts where the graph crosses the y-axis. So if we complete the following table, I'm going to do the first value here, and then I'll pause it so that you can fill in the rest of it. In the equation y equals 3 to the power of x, which was the graph I drew in blue, the value of a is equal to 1, the value of b is equal to 3, and the graph crossed the y-axis at 0 and 1. So again, I'm going to give you a couple of moments. What I would like you to do is I would like you to complete that chart. So again, you're going to pause, complete the chart, and start playing again. So if we look at the 4 graphs and where their y-intercept is, what do you notice about the value of y and the equation of the exponential function? And hopefully your answer is that they're the same. So what we're going to do is we're going to go a step further, and we're going to say, what is the effect of changing the value of a? So if I think of adding this a value, this y equals ab to the power of x. Well, what was a doing to the graph? A was actually a replacement. It was over on this side of the graph, which means that I have y being replaced with a 1 over a times y. This is a vertical stretch about the x-axis by a factor of a, because it's the reciprocal of the replacement value. So if f of x equals 3 to the power of x, it says write the following in terms of the function. So in other words, wherever I see an f of x, wherever I see a 3 to the power of x, I would replace it with f of x. So y would equal f of x in the first one. In the second one, y would equal 2 times f of x. In the third one, y would equal 5 times f of x. And then in the last, y would equal 0.5 times f of x. So what transformation is associated with these 3 values? It is the same transformation, because the 2 was with the y, the 5 was with the y, and the 0.5 was with the y. These are all vertical stretches. By a factor of. So in the second one, the stretch stretch factor, this would have been a 1/2 on the other side. The reciprocal would be 2. So it's a stretch of a factor of 2. With this one, I've got 5 times f of x. That 5 was originally on this side of the equation, which would have made it a 1/5. So I'm stretching by a factor of 5. And then the fourth one, this 0.5, when it was on the other side of the equation, was actually a 2. So this is a stretch by a factor of 1/2. So what is the effect of the parameter a on this graph? It is a vertical stretch about the x-axis by a factor of a. And at this point, we're looking at a values that are greater than 0. We're not looking at a negative a value. In all of these, the y-intercept would then be the value of a. Because in the y-intercept, if x is equal to 0, b to the power of 0 will equal 1. So if b to the power of 0 equals 1, 1 times a will be a. So the following page is a summarization of the characteristics that we've done so far. This would be a page that I'd want to earmark or put a tab or highlight. So if we look at the exponential function y equals ab to the power of x, the y-intercept, where does this graph cross the y-axis? At the value of a. So if there is no a value, it'll cross the x-axis or y-axis at 1. There is no x-intercept because the x-axis is a horizontal asymptote. If you think you can fill this out, pause, fill out the blanks, and then check to see if you've done this correctly. The domain for every exponential function is that x can be any real number. As an exponent, there is no restriction as to the type of exponent that I could have for x. The range is that y is greater than 0, and then y is an element of the real numbers. That happens when my a value is positive. What would happen if my a value was negative? So if I had a negative a value, that was a replacement on y. So if I get y equals negative a f of x, that means I'd have a negative 1 over ay. This negative would be a reflection in the x-axis. So if this is a reflection in the x-axis, that means that it's down below. It's in quadrants 3 and 4. So then my range would be all the negative y values. So y is less than 0. And that happens when my a value is less than 0. I need to fix this. This should be that it's less or greater than 0, not equal to 0. When the value of b is greater than 1, so such as 3 to the power of x, 10 to the power of x, 5 to the power of x, I get a growth function. And when the value of b is between 0 and 1, I get a decay function. It can't be equal to 0 and it can't be equal to 1. The value of b affects the steepness of the graph as x increases. So remember, this is my b value. When b is greater than 1, the graph rises more sharply as the value of b increases. So my 10 to the power of x graph is sharper than my 3 to the power of x graph. And when b is between 0 and 1, the curve falls more sharply as the value of b increases. So my 1/3 to the power, as the value of b decreases this time, my 1/10 to the power of x rises more falls more sharply than my 1/3 to the power of x. The value of a affects the vertical stretch of the graph. We don't worry about the idea of expansion or compression, so we're not going to actually look at these two values. But we are going to note that when the value of a is less than 0, I have a reflection in the x-axis because that a value is with the y. So it's replacing the y coordinates, which is what causes it to reflect in the x-axis. So we have some examples to go through where we describe the changes in the function. So it says, describe how the graph of the second function compares to the graph of the first function. So what I want to do is I want to identify replacements. What did I replace from this graph to this graph? Well, in the second graph, I have this 2. This 2 was actually with the y. So I replaced y with the 1/2 y. And then I have this x minus 2. So that's a replacement with x with an x minus 2. The 1/2 y, that's my vertical stretch. Vertical stretch by a factor of 2 because it's the reciprocal of whatever my replacement is. And then this x minus 2, that becomes a horizontal translation 2 units to the right because it's that minus. Okay, so if you want, take a look at B and see if you can do B before you watch the example through it. So if I look at my replacements on B, what did I replace? Well, I've replaced y with a y plus 4. This -2 actually would be written as -1 times 2 to the power of x over 5. So this -1 was actually with the y. It was replacing y with a -y. And then I replace x with a 1/5 x. That's how I get x over 5. So replacing y with a -y becomes a reflection in the x-axis. Remember our sort. We stretch or reflect and translate last. So I can do my reflection in the x-axis. This right here is a horizontal stretch. And this is about the x-axis by a factor of 5 because it's a reciprocal. And then my y plus 4, that is a translation 4 units down. Because that y plus 4 would have been a y minus -4, and the -4 pushes it down. So using that idea of replacements, we can now answer the question of why the graph of y equals 1/3 to the power of x is a reflection in the x-axis of the graph y equals 3 to the power of x. And to do that, what we're going to do is we're going to use common bases. So if I want to change 1/3 to the power of x into a base of 3, how would I do that? What exponent to the power of 3 would give me 1/3? The answer, -1. So if I replace this with a negative 1 to the power of x, I get 3 to the power of negative x. So my replacement is I replaced x with a negative x, which is a reflection in the y-axis. Okay, we have one last example. Consider the function f of x equals 4 to the power of x plus 2 minus 6. Without using a graphing calculator, determine the following. So the domain and the range, the y-intercept, and any asymptotes. So if I take the function y equals 4 to the power of x as my original, and then look at what happened here. Well, this minus 6 was with the other side. So I had a y plus 6 at one point in time, and then a 4x plus 2. So this x plus 2, that's a translation to left, and this y plus 6 is 6 down. So the domain. The domain of an exponential function is the element of the real number system. That's not going to change if I move the whole thing 2 units to the left. So the domain is still going to be that x is an element of the real numbers. The range of my function. An exponential function has a range greater than 0. But I moved this thing 6 units down. So my range now is going to be greater than 6. The y-intercept, remember the y-intercept is the value of a. Or sorry, the y-intercept is when x equals 0. That's a better one. So if I let x equal 0, I will get that y is 4 squared minus 6, which becomes 10. So the y. So C says, what is the equation of any asymptotes of the graph of the function? Well, the only asymptote in an exponential function is a horizontal asymptote. And so with my horizontal asymptote, in my regular function, it's the x-axis. But again, remember, I shifted this thing 6 units down. My horizontal asymptote matches up to my range. If my range is greater than 6, or sorry, that's 6 down, that should be negative 6. So y should be greater than negative 6, sorry. So if my range has to be greater than 6, my asymptote is then going to be equal to 6. So the questions that I would like you to work on, questions 1, 3, 4, and 5, 7, 8, 9, 10, and 11. So just let me double check those. Okay, I'm going to eliminate questions 3 and 7. So your questions now are 1, 4, 5, 8, 9, 10, 11.